Without any further ado, Dr. Geoffrey Ellis is our speaker tonight. He is a research geologist and the project chief of the Potential for Geologic Hydrogen Gas Resources project within the Energy Resources program of the U.S. Geological Survey. He is also an affiliated faculty member in the Department of Geology and Geological Engineering in the Colorado School of Mines and the chair of the Hydrogen Resources and Storage Committee within the Energy Minerals Division of the American Association of Petroleum Geologists. He holds an AB in Geological Sciences from Cornell University, an MSc in Geochemistry from the Colorado School of Mines, and a PhD in Marine Geology and Geophysics from the University of Miami. I also like to say that in the past couple of days, I've been watching as many scientists give TED Talks on this topic to make sure I had some understanding of it and I could ask some smart questions. And about half of them all mentioned Dr. Geoffrey Ellis. So we know that we have a good speaker for us tonight. So Dr. Ellis, thank you so much for taking the time, especially on the road, to be here and share your expertise with us. Please take it away.
Okay. Well, thank you, Rich, for that really kind introduction and for the invite to speak with the group tonight. Really happy to be with you all and excited to talk about this topic that, as Rich mentioned, I think has the potential to really be a game changer. And we're really at the very earliest stages, just beginning to understand it. And there's a lot that we need to learn, but there is certainly a lot of potential here, I think. So what I'd like to do in the talk this evening is to start out kind of high level, talk about just the basics of energy consumption and how it relates to economic development, and then how this ties into climate and where we are in terms of our climate situation. And then more specifically, we'll move into talking about how hydrogen can play into our energy mix. And also about this notion of natural hydrogen. How does it occur on Earth, and how could it be part of our energy resources? And what is the potential for natural hydrogen to contribute as an energy resource? Then we'll talk a little bit about some of the environmental health and safety concerns surrounding hydrogen, and then we'll wrap up. So let's start by looking at this. This is a chart showing the historical development of energy resources over the last 200 plus years, going back to about 1800. And what you can see here is that in the first half of the 19th century, we were still reliant exclusively on traditional biomass, basically burning wood for our energy resources. And then in the second half of the 19th century, we began to develop coal resources, and steam power became an important part of our energy and our economies. And so we see the development, the rise in coal as an energy source. And then as we get into the 20th century, we start to see additional energy resources coming online, oil and natural gas. And then finally, in the second half of the 20th century, we see some of these other energy sources like hydropower, wind and solar and so forth, nuclear. And there's a few key items to notice, I think, in this figure. The first one being this dramatic rise in energy consumption in the second half of the 20th century. And also the fact that you'll notice that every time a new energy resource has been developed, it simply adds on to the prior energy that's being consumed. We've never actually phased out any energy. Every time when we found oil, we just started using more energy and added on top of the coal that we were burning. And likewise with natural gas and hydroelectric and solar and so forth. I mean, and you will note that there's a small dip in energy consumption in 2020, which is related to the global pandemic. But now, since then, we've rebounded, and all these trends have continued upwards along this kind of trajectory. And the one exception here is that you'll note that the consumption of coal in the last few years has started to level off and even begin to decline. And that this is the first time in human history that we've actually started to phase out one source of energy. But other than this, every other energy resource has just continued to increase. And the other thing to note here is that the vast majority of our energy today comes from three sources: from coal, oil, and natural gas. So another important piece of the story, I think, is looking at economic development. And so this is a chart showing gross domestic product per capita, which is a proxy for economic development and standard of living that people have in a country. And on the y-axis, we have energy use in tons of oil equivalent per person. And then the circles represent countries around the world with the size of the circle proportional to their populations. And you can very clearly see that with increasing GDP, with higher standards of living, we use more energy. This is not a big surprise. What's I think of particular note here is that you'll see that India and China both have very large populations, and they're down here at the low end of energy consumption. But they certainly aspire to having a higher standard of living that is enjoyed by us in the U.S. or in other parts of the world. And so almost certainly as they develop further, their energy consumption will go up several fold. And so we're going to have this growing demand for energy in the coming decades. Then the final piece of the story here is this plot showing both the trends in measured atmospheric CO2 and the global surface temperatures around Earth over the last more than 100 years. And we see this CO2 is plotted here in blue, and we can see that around 1900, we had less than 300 parts per million of CO2 in the atmosphere on average. And in the recent years now, we've crossed over this 400 parts per million concentration of CO2. The physics of this is very well understood. That carbon dioxide is a potent greenhouse gas, that it has the potential for trapping heat inside our atmosphere and warming up the planet. And it's no surprise then when we look at the temperature rate or the temperature data for the surface of the Earth, shown here in red, clearly we see a correlation here where as CO2 goes up, the Earth is warming. So this leads us back to our energy story and the fact that currently we are primarily relying on natural gas, oil, and coal to supply our energy needs today. And this plot shows these various different energy sources, both non-renewable and renewables, plotted against their life cycle greenhouse gas emissions. This is in equivalent grams of CO2 per kilowatt hour of electricity. And so you can see that these natural gas, oil, and coal are all very carbon intensive fuels. We generate a lot of CO2 when we burn these fuels. Essentially, we've been mining carbon from the subsurface and putting it up into our atmosphere when we do this. And so it's clear now that in order to address the climate challenge, that we need to transition away from these traditional fossil fuels and more towards renewable type sources like photovoltaic, solar, or geothermal or hydrothermal power. But there are some important considerations about these renewables. This is a graphic just showing a variety of the most common renewable energy sources. And if we look at their applications that they can be used for, the one commonality we see is that they're all good for generating electricity. Some of them have the ability to do some heating and cooling or maybe a little bit of transportation. But in general, renewables are really good at making electricity. However, there are certain parts of our economy that are really difficult to electrify. So things like steel manufacturing or cement or petrochemical manufacturing, as well as aviation or shipping, are really difficult to electrify. I think it's commonly that we will not be able to be flying 747s powered by batteries crossing the Atlantic Ocean, and so we will need some other sort of energy supply that can meet that demand. And so it's thought that hydrogen may be the best solution to decarbonize some of these hard to decarbonize sectors of our economy. So what is hydrogen exactly? It's actually the most common element in the visible universe. In its native state, it exists as a diatomic molecule, hydrogen H2. And it can be used to generate heat or electricity. You can combust it and make heat, or you can actually just put it through something called a fuel cell, where you put hydrogen and mix it with air, and you get electricity out and water, basically pure water. And so we can actually produce and store and transport hydrogen without generating any toxic pollution or CO2 emissions. And it also has 3 times as much energy per unit weight as gasoline, diesel, or jet fuel. So really makes it an ideal fuel for applications where weight is a consideration, like aviation. It can also be very efficient in delivering electricity at greater than 60% efficiency through fuel cells. And it can also be pumped at similar rates to liquid hydrocarbons. So if you're familiar with our electric cars that we have today, many of them have to be plugged in and charged overnight in order to have their full range, as opposed to our cars where we can just fill them up with gasoline in a matter of minutes. And so hydrogen actually can be pumped at the same rates that we can with other liquid fuels. And it also burns at a very similar temperature to natural gas, which can have important applications. So, in addition to decarbonizing these hard to decarbonize or electrify parts of the sector and parts of our economy, another important potential application for hydrogen is actually in replacing natural gas as an energy resource. And so here in the U.S., we have 2.5 to 3 million miles of natural gas pipelines spanning the entire country, as shown here in this map. It's actually more than 6.5 times more natural gas pipelines than our interstate highway system. And we've made an enormous investment in this natural gas infrastructure. Over $500 billion has been spent, with more than $200 billion just in the last decade or so. And half of the U.S. homes are using natural gas either for heating, cooking, drying clothes, or all of those applications. And so to replace that infrastructure and upgrading our electrical infrastructure to replace natural gas with electricity is going to be really expensive and also very time consuming. If we're going to try and get to net zero emissions by 2050, it's going to be a challenge to get there and replace all of this infrastructure. However, you can actually blend hydrogen into natural gas and use it the way we currently are using natural gas. And in fact, it's thought that we could put up to 20% hydrogen could be mixed in with our natural gas system right now without any changes to our infrastructure. And that would actually that would reduce about 5% of the U.S. CO2 emissions just by blending hydrogen into our natural gas system. Now, you wouldn't get the full amount of energy return by doing that. Hydrogen only has about 1/3 of the energy of natural gas per unit of volume. So if you were to put 20% hydrogen into our natural gas system, we'd only get about 87% of the energy back. But that still would be something that we could live with. We could work with that very well. So where do we get hydrogen then today? We currently globally we make about 100 megatons or million metric tons of hydrogen per year, and it has to be made right now. It's made from fossil fuel sources, either natural gas or coal. That's mixed with water and heated up over a catalyst, and then you can form hydrogen. But in the process of doing that, to make 1 kilogram of hydrogen, you end up generating about 12 or 13 kilograms of CO2, which currently is going directly into the atmosphere. And as I mentioned, that with this need for hydrogen to supply the energy for these hard to abate sectors, it's expected that the demand for hydrogen will increase by more than 4-fold by 2050 in order to meet these net zero emission goals that have been set forward. And it's thought that this is going to come from a combination of so-called blue and green hydrogen. The green hydrogen is hydrogen that's generated by splitting water with these fuel cells, but the electricity has to come from renewable sources. And then Blue hydrogen is hydrogen that's made from fossil fuel sources like natural gas, but that CO2 is then captured and either reused or is sequestered and stored somewhere. And so it has no carbon emissions associated with it. But these these sources of hydrogen, in order to get to this over 400 megatons per year of blue and green hydrogen that's projected to be needed by 2050, we are going to have some challenges to get there. So in order to make all of this blue hydrogen, we are going to need to store, capture and store around 1,200 megatons per year of CO2 by 2050. And in 2023, globally, we were storing about 50 megatons per year. And so we have to ramp up our carbon capture and storage by several orders of magnitude in order to get to this level. And that's just for making blue hydrogen. And people are talking about sequestering CO2 for many, many other applications. So we have a long ways to go to get to that target. And to get to making the amount of green hydrogen that's projected to be needed, we are going to need about 12,000 terawatt hours of new renewable electricity just to make this green hydrogen. And in 2022, the total global renewable electricity amount was about 8,500 terawatts. So we're going to need about 1.5 times more renewable electricity just for making green hydrogen. And that's not renewable. That doesn't account for all the renewables that we're going to want to power our electric cars and our heat pumps that are going to heat and cool our homes and everything. And additionally, the electrolyzers that are used to split water and make hydrogen, they use a fair amount of rare minerals, or rare elements, things like platinum and iridium. And so we're going to need to really ramp up the amount of mining that we do to build all these electrolyzers to make this green hydrogen. And so there's some serious challenges that we face in trying to make all this blue and green hydrogen. And importantly, in all this discussion about hydrogen as an energy resource, it's viewed exclusively as a medium for energy storage and transport and not a primary energy resource. So it's not like coal or natural gas that we can collect from the subsurface and then burn it and get the energy out. This is something that you have to put energy in to make the hydrogen and store it and transport it around, and then later you can get some energy back. But there's always some inefficiency in that because you have to put a significant amount of energy into making it and moving it around. And a question that we're going to spend the rest of the evening talking about is, what is the resource potential of natural hydrogen? So natural hydrogen actually occurs, we're surrounded by it here on Earth. The air that we're breathing right now contains on average about 0.5 part per million of hydrogen. The world's oceans are super saturated with respect to hydrogen. In soils, we often find tens or hundreds or even thousands of parts per million of hydrogen gas in the soil. And deep mines and boreholes very frequently encounter hydrogen gas, often at percent concentrations. This is a map showing documented observations of hydrogen at greater than 10 mole percent from all over the world. And you'll note that there's a high density of observations in Eastern Europe and Russia. And this is actually because there were research groups that were very active in those areas and went out and made a lot of measurements, and they found a lot of hydrogen in all these places. And most of the rest of the world has barely been explored. So it's almost certain that if we actually went out and looked for it in all these other parts like South America or in Africa, that we would find hydrogen just as commonly as they have in Eastern Europe and Russia. So where's this hydrogen coming from? Well, there are dozens of natural processes that are known that can generate hydrogen. One of the big ones that we observe that can generate large amounts of hydrogen is this reaction of water with iron-rich rocks, something that that we typically refer to as serpentinization. It's shown here in this schematic down below. And this is essentially the process of rust, where you have iron reacting with water and forming iron oxides. And in that process, you strip the oxygen away from the water and you release hydrogen in the process. But there are many, many other processes that are both abiotic as well as biological ones, and also physical chemical processes where you can have gases coming out of solution in various settings. So there's really no shortage of processes that are generating hydrogen on Earth. If we look at the median concentration of hydrogen by a variety of geologic settings around the world, what we note is that the places that have the highest concentration of hydrogen are associated with what we call hard rocks, these crystalline rocks, volcanic magmatic settings, or mid-ocean ridges. And if we move off to the far right here, where we see the lowest concentrations, you note that that's actually associated with natural gas. And in fact, we've drilled hundreds of millions of oil and gas wells all over the world, and it's very rare to find more than maybe 1% hydrogen associated with natural gas. And because we don't find hydrogen associated with natural gas, geoscientists have assumed that even though hydrogen is very abundant on Earth and we see it in all these places, that there must be something about it that prohibits it from forming accumulations like we get with natural gas and with petroleum. And the thinking is that it's because it's a very small molecule, it can easily diffuse through even the tightest rocks, and it's also very reactive. There are many microbes that like to consume hydrogen, or other abiotic chemical reactions that can consume hydrogen, and so that it probably just leaks out and gets consumed, and we just simply can't get accumulation of hydrogen, even though it's very, very abundant around the Earth. But there are some very good reasons to question this notion that it's so diffusive and leaks out, and you just can't get these accumulations. And the first of these is that the places that are most likely to generate natural hydrogen, these are these hard rock places that we just talked about, with crystalline rocks or volcanic magmatic settings. These are not the places where oil and gas is found. And so, in fact, the oil industry really doesn't do any exploration in these kind of settings where hydrogen is most likely to be generated. The other thing is that petroleum exploration doesn't target hydrogen, and so they're not looking for it. The exploration strategies are not designed to try and find it. Oftentimes, they don't measure for it, and they're exploring mostly in these sedimentary basins. That's where most of the oil and gas is accumulated. And this is really not the place that we would most expect to find natural hydrogen being generated. Moreover, the process of generating hydrocarbons from organic rich rocks is actually a hydrogen limited process. When geologists want to measure the quality of a rock and its potential for generating petroleum, they actually measure something called the hydrogen index, which is a proxy measurement of how much organic hydrogen is in that rock. And what this means is that if you have an external source of hydrogen, say there were some deep source of hydrogen and hydrogen was migrating up from the subsurface, if it encountered organic rocks that were generating hydrocarbons, that hydrogen most likely would get incorporated into hydrocarbons. So that hydrogen would get turned into methane, say. And so we really shouldn't expect to find hydrogen associated with hydrocarbons. There's really a good reason to think that you should never find it there. Now, many of these hard rock settings that I mentioned, these volcanic magmatic settings, these are places where mining companies are very active. There are a lot of mineral resources that are located in these kind of geologic settings. But the mining companies, they rarely look at gas composition. They often will measure gases as a safety hazard. They frequently encounter explosive or flammable gases in their exploration activities. And so they'll measure just using an instrument that says, oh yes, there's explosive gas here, be careful, but it doesn't tell them exactly what the composition is. They don't know if it's hydrogen or methane or propane or some other flammable gas. And so the bottom line here is really that we just simply haven't been looking for hydrogen in the right places with the right tools. So in that context, I want to really interesting site in the country of Mali in West Africa. And the story here dates back to 1987, when there's a small village north of the capital of Bamako, where they were relying on hand-dug wells to provide water to the village. And during prolonged periods of drought, the wells were frequently running dry, and they were being stressed by lack of water. And so they eventually got some international aid to fund the drilling of a water well for this local village. And they hired an Italian drilling company to come out and drill a water well for the village. And they began drilling in a few locations, looking to where they could tap into the aquifer. And in the first few places they drilled, they weren't able to find water, and they moved on to other places. And while they were drilling at another site, a local villager went over to one of these holes that was left in the ground where they had initially been drilling for water, and noticed that there was some gas coming out of the ground. And so he went and got one of the drillers and said, "Come check this out. There's gas coming out of the ground." And so the driller went over to investigate the hole, and he happened to be smoking a cigarette at the time, and leaned over the hole and ignited the gas and actually blew himself up. But fortunately, he was not seriously injured or killed. But it took the villagers weeks to put out this fire from this hole. And they eventually got the fire put out, and they plugged the hole, and the drillers drilled in another location and found water, and they put in a water well, and they left. And so it was about 25 years later, in 2012, when an oil and gas company that was familiar with the story of this flammable gas that came out of this hole, they went back to this site with the intent to drill a proper natural gas well and to produce natural gas from this site. And so they drilled the well, and they completed it, and they started to produce the gas. And when they tested the composition of the gas, they were shocked to find that it was actually over 97% hydrogen gas, not methane, not what we would call natural gas, but this was hydrogen gas, almost pure hydrogen gas. And so they after drilling this initial well, they went back and they did an extensive exploration campaign, doing geophysical techniques to try and image the subsurface. And they've identified now a number of stacked reservoirs that are charged with hydrogen, shown in this cartoon down here below. And that initial discovery well is still producing hydrogen today. It's being used to generate electricity for the village. Initially they brought in an internal combustion engine generator that had been converted to run on hydrogen, and they ran that for many, many years. And just recently, last year, they replaced that engine with a fuel cell, because they wanted to test to see whether the purity of the gas was sufficient that they could simply take the gas right out of the ground and run it right through a fuel cell and make electricity. And it's been running now for about a year, I think, and successfully making electricity for the village. And there's still a lot we don't know. We really don't know exactly what the source of the hydrogen is at this site. And we're not entirely sure how much hydrogen is there, but it's estimated there may be as much as 60 billion cubic meters of hydrogen in this one gas field, which would make it a medium-sized gas field if that were a natural gas field. So in the wake of this discovery in Mali in 2012, as news of this got out to the broader geoscience community, exploration now has started in other parts of Africa, and it's spread to Europe, and now to really every continent around the world. In the first well that was drilled explicitly targeting natural hydrogen was drilled here in the US in 2018, and did encounter hydrogen in that hole. And where a number of wells have been drilled since then in the U.S., mostly in Kansas and Iowa, in an area called the Mid-Continent Rift. And there are more wells that are planned to be drilled later this year. Also, a couple of wells that were drilled late last year in Australia at an interesting site where some oil and gas companies had actually been drilling 100 years ago and had found hydrogen in these holes, but they walked away from the site because they were looking for oil, not hydrogen. And recently people went back to company records and recognized that they had found hydrogen there. And when they re-drilled those sites, they found similar concentrations, over 70% hydrogen in these wells. And another really interesting project that's in the planning stages is in Oman, where there's some one of the most extensive amounts of these iron-rich rocks that have the capability of generating hydrogen. They occur in a very large amount in the country of Oman, and so there's a project that's being planned to do something called stimulated hydrogen at this site, and I'll talk about that more a little later. But first, I want to come back to this notion about natural hydrogen as a resource. And the question really is, how much hydrogen could really be down there, and could this really constitute a resource? And so we come back to this histogram here showing that in order to get to net zero, we think that we need over 400 megatons per year of hydrogen. And there are estimates of what the annual natural production of hydrogen around Earth might be. It's thought that it's currently maybe around 23 megatons per year that is being generated on Earth. And so if we put that in context with this 430 megatons per year, that would only be about 5% of what we think the global demand is going to be. And that would be 5% if we could actually find all of that hydrogen and produce it all. But of course, that is really not practical. We would only be able to capture just a small fraction of that. So it would seem that if we have to rely on how much is just being generated naturally every year, that hydrogen probably wouldn't be much of a resource. But it's important to note that the resource potential isn't just dependent on how much is generated every year, but how much could actually get trapped in the subsurface and how long it could be held there, and whether it might be consumed by reactive processes, and then how efficient we could actually be at finding it and producing it. And so to try to get at this question of how much resource might actually be there, I've been working with a colleague of mine at the USGS to put together a simple model of the entire globe. It's shown here schematically in this cartoon in the upper right, where we have a source of hydrogen somewhere deep. We don't know exactly what the source is, but we know that it's being generated in the subsurface from a variety of different processes. And it will migrate up through the subsurface, and some of it will get held up in traps, and some will go straight to the surface. And along the way, it will be consumed by abiotic processes or biological processes. And some will leak. Once it gets into these traps, it's not going to stay there indefinitely. It will leak out over time. And then eventually we can perhaps go out and explore for it and produce it. And so for many of these components in the model, we have an incomplete picture of hydrogen. We know a little bit about how hydrogen behaves, but not fully. And so we rely on also on analogs from other fluids in the subsurface, things like petroleum and helium, to constrain what the inputs to this model might be. And then we can assume that this natural system has been in place for millions of years. So we're currently now at a steady state. And then we can run a Monte Carlo of all the range of input values that we think are realistic for this model, and we can calculate how much might actually be trapped in these reservoirs. And so that's what's shown in this histogram on the lower right. And the first thing to note on the results here is that the uncertainty is very, very large. We're talking about 7 orders of magnitude. Anywhere from maybe only thousands of megatons in the subsurface to potentially billions of megatons. And the mean value is on the order of, say, a few million megatons. I think the P50 is around 5 million megatons in the subsurface potential. But the other thing to note here is that most of this hydrogen is likely to be inaccessible. This is model of the entire Earth's crust. And so this includes places that are very far offshore or very, very deep, that would just never be economic to be produced. And many of these accumulations might also be very, very small and just not worth drilling. But as a thought exercise, I said, well, let's assume that there's maybe 5 million megatons. That's within the realm of possibilities. And if we could just find and produce 2% of that, that would represent 100,000 megatons. And that 100,000 megatons would actually supply all of that 430 megatons per year that we've been talking about for a couple of hundred years. And so it seems that it's very likely that there's a large amount of hydrogen in the subsurface And if it's in accumulations that we could find and produce, it could very easily provide all of the hydrogen that we think we need to get to net zero. And so the key question really is not, is there hydrogen down in the subsurface? The question is it in accumulations that we could find and produce economically? So to try and answer that question about is it in accumulations that we could find and produce, we need some kind of geologic model. And so we've been working in the USGS to develop a geologic model that we could use to better understand the resource potential. And to do that, we're starting with something that's called the petroleum system model. And this is a geologic framework that's been developed over many decades, and it's been used very effectively by the oil and gas industry to find hydrocarbons. And the petroleum system is made up of a source rock and then has migration pathways that the petroleum will follow after it's been generated. And then you need reservoirs where the fluids can get accumulated and seals that can hold it in place. And then we need to understand the potential for that fluid to be preserved and understand the timing of all of the events that come together here. And so we can take that same conceptual framework, but we have to modify it and adapt it for hydrogen. And so we know that there are sources of hydrogen and migration pathways and reservoirs and traps and seals, but they're not exactly the same rocks or the same processes that we know for petroleum. And so we're working now on trying to better understand what are the source rocks? Certainly, although there are dozens of natural processes that can generate hydrogen, not all of them generate very large quantities. And so our focus is really on the processes that can generate the large amounts of hydrogen that could actually produce a resource. And then trying to understand all of the other, all the variables that affect how these processes work in the subsurface. I also want to point out that how we define this hydrogen system depends in part on how we think that we are going to be able to produce natural hydrogen. And there are three ideas that have been put out there about how this process might work. And so the first is what I refer to as natural accumulations. And this is a situation where you have an external source of hydrogen. So for example, you may have water that's getting down deep and encountering iron-rich rocks, and that water gets reduced by the iron and generates hydrogen. And the hydrogen migrates away from that source rock and up into the upwards in the subsurface, and encounters some porous rocks that could form a nice reservoir, and it has a seal on top that can hold it in place. And then we can find it and drill into it and produce that fluid. And so this would be very directly analogous to a conventional oil and gas accumulation. And in that situation, we need to understand the source and migration pathway, reservoirs, traps, seals, all of the elements of our petroleum system would all come into play for this hydrogen system. But it has been suggested that because hydrogen can be generated relatively quickly, the process of water reduction by iron-rich minerals actually happens in real time. We can observe it in the laboratory on a period of days or weeks, and we can go out into natural settings like mid-ocean ridges and see it happening, again, in real time. As opposed to oil generation, which takes millions of years to happen. And so because hydrogen can be generated so much more quickly, it's been proposed that we might be able to just drill down into rocks that are currently generating it or along fault zones where hydrogen is migrating up from deeper sources and produce it as it's being generated. More analogous to, say, a geothermal resource rather than oil and gas. And then a third idea is that we might actually be able to engineer a system where we could actually stimulate hydrogen generation. And there are a number of different ideas that are out there that people are looking into. In fact, the US Department of Energy has now funded a $20 million research program into trying to figure out how to stimulate natural hydrogen generation. But one rather simplistic scenario that you can imagine is you can have iron-rich rocks that they're at the right temperature, reducing the water, but they simply don't have water moving through those rocks. And so if we were just to drill down into them and fracture them and inject water, we could just inject water into the rock and the water would get reduced and make hydrogen, and we could extract hydrogen right out of those rocks. And importantly, those model calculations that I just showed you, where there might be potentially millions of megatons in the subsurface, those model predictions are only for these natural accumulations. That doesn't account for these other two types of generation. So if we could actually make these other two forms of hydrogen work, then that would just be even more resource that potentially could be realized. But it's important to note that these are really just hypothetical concepts right now. We're really in the very earliest stages of trying to understand whether these other types of hydrogen plays might work. But this accumulation model, this is actually what we already know exists in Mali, and we know we have other gas accumulation, not only natural gas, but also there's helium accumulations and CO2 and nitrogen accumulations subsurface. So this system seems to be something that we have quite a bit of knowledge about and more confidence that this could actually work. Another thing that we're working on in the USGS, in addition to our development of this hydrogen system model, is now we're also working to see if we can try and map out where are the best places in the United States where we could go looking for hydrogen resources. And so we're taking our hydrogen system model and then identifying proxy data sets that we can use to map out where would maybe good rocks for forming seals or traps or reservoirs or source rocks might be. And then we're trying to account for the uncertainty in the data and the model, and then developing this map for the lower 48 states. And so we have now built a model that's shown here schematically, where we have mappable data layers that we show in these pinkish boxes. And then we are combining them with an algorithm to then calculate an interpreted value that then we can combine with other interpreted values, and combine these all together to come up with a net prospectivity. And for each of the inputs to the model, we assign something called a chance of success. It's essentially a weighting where we think that some things might be more viable in producing a hydrogen source than others, for example. And so we are still working on this, but this table shows all of the input data layers that we currently have and some of the chance of success values that we've been assigning. But this is still very much a work in progress. So we're not at that final stage yet. We're adding new data layers and also refining some of the existing data that we have, and looking at this initial model will be simply a deterministic map based on fixed values that we have for these chances of success that we assign to the input values. But we're also looking at doing a probabilistic approach where we could actually put a range of values on each of the inputs and then run a Monte Carlo on that and actually calculate a P10 and a P50 and a P90 for prospectivity across the entire United States. And we're also looking at putting out an executable computer code that people can put their own data sets into to use for other parts of the world, or if they just want to do their own work with the data that we use for the US. And also we're thinking about trying to put together a web-based interactive map that would allow users to customize their model for what they think is important for geologic hydrogen accumulations. So this is something that we will be coming out with by the end of this calendar year. So stay tuned for that. It should be a really interesting product. But I want to talk now about some of the challenges that are associated with using hydrogen as an energy source. At the outset, I was touting all the great benefits of hydrogen, and it certainly has a lot. And there's a lot of interest in using hydrogen because of its flexibility and many of the other great properties that it has. But there are some challenges. One of the big ones is that although I mentioned that hydrogen has a very high energy density per unit mass, and you can see that in this chart here, that this is gravimetric density versus the energy density on a weight basis versus energy density on a volume basis. And so hydrogen is very good on a weight basis, but it's very poor on a volume basis. And so what that means is that if we want to transport it over long distances, we need to compress it or liquefy it, or freeze it, or convert it to some other chemical form to make it more efficient for transporting over long distances. And so in that process, you have to put more energy in to transport it, which then reduces the efficiency of the energy overall. Another one of the challenges of hydrogen is that hydrogen has the potential to cause embrittlement in steel. It gets into natural defects in the steel matrix itself and can then cause fractures to open up, and then eventually the steel will fail. We have been making and handling, transporting, and storing hydrogen for many, many decades. And so this embrittlement issue is well known, and there are higher grades of steel that are more impervious to this embrittlement issue. But for example, with our existing natural gas pipeline, if we put in too high a concentration of hydrogen into our pipelines the way they are today, that very likely would lead to embrittlement and failure and leaks and so forth. And so we would actually need to upgrade the steel pipes, or in Europe, they're currently doing research on looking at different types of polymers that they could use to coat the insides of pipes, so that they may be able to just actually spray the inside of the pipes with a plastic coating, essentially, that would then make it inert. So there are ways to address this issue, but it is an issue that we need to be cognizant of. The other thing is that hydrogen itself is not a greenhouse gas, but it does have indirect greenhouse gas effects. And so this cartoon here is illustrating that when hydrogen, when it gets into the atmosphere, it very rapidly diffuses up into the stratosphere. And in the stratosphere, it will react with hydroxyl radicals to form water. And the issue is that these hydroxyl radicals are actually the primary mechanism for removing methane from the stratosphere. And so if we have more hydrogen getting up into the stratosphere, that is going to consume these hydroxyls, and then that will actually increase the residence time of methane in the stratosphere, which then would have a global warming effect. It also, hydrogen can form tropospheric ozone, which is a greenhouse gas. And then also when the hydrogen reacts with these hydroxyls, it forms water, which is a very potent greenhouse gas. So there are some very real concerns about stray hydrogen emissions. If we build out this very extensive network of pipelines for hydrogen, we have to be sure that we keep it very tight and we don't have a lot of stray emissions getting into the atmosphere. But another important consideration is the natural global hydrogen cycle in our atmosphere and in the subsurface. And this is something that has been studied for a number of years, but there's a fair amount of uncertainty about it. It is well known, the photochemical processes in the atmosphere that generate hydrogen, as well as natural processes in the ocean that can generate hydrogen, and then the anthropogenic sources from fuel use that humans are doing. These are all sources of hydrogen into the atmosphere. And it's known fairly well the amount of hydrogen that's removed from the atmosphere by these hydroxyl radicals. But the other sink for hydrogen is uptake by soils. And it is documented that microbes that live in soils are able to pull hydrogen out of the air and consume it. However, this component of the global cycle is not very well constrained. And basically, the number that's put on here is used just to balance out the whole cycle. And so when the numbers don't add up, they say, okay, well, there's probably just more hydrogen getting taken up by soils. And importantly, in all of this, in this whole model, there's no consideration for any flux of hydrogen actually coming out of geologic sources. It's thought that the earth and soils just take up all the hydrogen. But in fact, as I showed you earlier, we have all these sites where we have 10% hydrogen observed at the Earth's surface. And there are many, many sites that can be a significant flux of hydrogen to the atmosphere. And so this is something that's not well constrained, that really needs to be worked out, especially if we are worried about what additional fluxes of hydrogen from anthropogenic sources might be. We really need to better understand what the natural cycle is, so that we can really understand what the magnitude of impacts of additional anthropogenic activity might be. So with that, I'll just leave you with some of the takeaways that hydrogen is likely to be really important to reach our net zero carbon emission goals. But making low carbon hydrogen may be challenging. With the current technologies we have, there's some serious obstacles that we face. There's a lot of research going on in these areas, and hopefully we'll have some big breakthroughs, but it's going to take a lot of work. But we do know that there are large quantities of natural hydrogen that exist in the subsurface. But what is not known is whether it exists in accumulations that could actually be economically produced. But we're working on it. The USGS, we're doing research to improve our understanding of what the resource potential might be, and mapping out where we think the best places to begin looking for natural hydrogen would be. So with that, I'll leave you with, I want to acknowledge my colleagues from the energy program that have done a lot of work on our prospectivity mapping work, and also want to just highlight this really interesting article that came out in Science magazine last year. That they did a very nice job of summarizing the story of what we know about natural hydrogen, that I would recommend. If you haven't read it, I would highly recommend it.